Hello, Calc. We're going to look at a related rates problem tonight that we have to tweak a little bit from what we've seen in class so far. We've done leaning ladders, and we have done the classic, what else is there that we've done? The spherical object that was gaining or losing volume, and the other classic one escapes me right now. But we're going to do another classic one, but this one is going to have two variables in it. So we're going to start this one, and this is the October 31st, the October 31st edition. And we're going to look at a related rates problem with a cone. So that's pretty common. So we're going to have a cone, and the cone has a diameter, and the diameter of the cone is 10. So from here to here is 10 feet, and the cone is 12 feet tall. And inside of the cone there is going to be some sort of liquid, and that liquid is going to be changing, the height of that liquid is going to be changing because there is coming into the cone a stream of water, and that's coming in at 10 cubic feet per minute. So it's filling up this cone that is 12 feet high and 10 feet in diameter. So as we look at that, we're interested in the height of this water level or liquid level inside the cone. So let me give you the question. Find the rate I want you to find the rate of change of the water depth when it is 8 feet deep. All right, with that question, let's go ahead and make some observations. We're not usually interested in diameter, so we're going to switch to radius. So I'll put that in the picture. So 5 feet, and I'm just going to erase the 10. And I am also going to give a radius on the water level. There's a cone inside a cone. So the water level also has a circular top, and that has a radius. I'll call it small r, and it has a depth. I'll call that small h for height. So that is all the numbers that were known, and we've gone ahead and labeled things that are going to be useful to us. So when we do a related rates problem, the first thing we need to do is figure out an equation that will help us relate all these variables. Well, since the volume of a cone is involved, as the water pours in, the volume of this cone inside the cone will be increasing. So let's go with the volume. Volume of a cone is 1/3 pi r squared h. And therein lays our dilemma for tonight. There's a variable here, v, there's a variable here, r, and a variable h. Do you see how these are variables? Because as this water enters the cone-shaped container part with water in it, the radius will be increasing and the height will be increasing. So everything's changing. So it is quite amazing that we can do this problem where we have all these things changing at once, and yet we can stop it in a moment of time and find one rate all by itself. So let's do that amazing task. So what derivative are we asked to find? It says find the rate of change of the water depth So we call the water depth h. So putting that in derivative language, we're going to find dh dt, the change in height with respect to time. And remember, there's always a when. We're going to find a derivative when, and in this case, when h is 8 feet. All right, so let's see how that plays out. Here we are with our equation, and I'm going to take the derivatives across, and I get the derivative of v is just 1, but I'm going to call that, instead of writing the 1, it's followed by the chain rule, which is dv dt. Are you getting used to the chain rule? Should become pretty second nature. Maybe not quite yet, but soon. So the unwritten one is there, 1 dv dt equals, now the 1/3 and the pi are constants, and then we hit a product. And I really don't want to do the product rule, and I have a way to not use it. So I'm going to come over here and come right down here, and I'm going to figure out a way that I can express r in terms of h or h in terms of r so that I only have 2 variables. I'm good at working with 2, but throwing in the third is a little complex. So let's go ahead and look at this picture and see how all the numbers relate in a different way. And I see a radius up here that is constant 5, but this radius could be whatever it is when at the moment we stop the problem. I see a constant height of 12, and this h is varying. So let's make a statement, because no matter where we look at this picture, wherever the height of the water level is, we still have a right triangle within a right triangle. So Miss Grace would be very pleased to know that you recognize those are similar triangles, and their sides are proportional. So we can say 5 is to r, 5 is to r as 5, those are the 2 radii, and then the heights. 12 is to h. So at any point in time, those that right triangle within the right triangle are similar triangles, and they are proportional. So I set up this proportion, cross multiplying, I get 5h equals 12r. Now is our moment of decision, because I have to figure out whether I want to solve this for h and have it in terms of r to substitute in for h, or should I solve it for h and substitute it in, should I solve it for r and substitute it in, or the other way around? So what I'm going to do is, because I'm looking at what I know, in this problem h equals 8 pi. So if I substitute in for h in terms of r, then I lose my h altogether. So let's go the other way. Let's solve this for r in terms of h. So I'm going to get r by itself, and I divide both sides by 12. I get r equals 5/12 h. r equals 5/12 h. All right, so wherever there is an r in this problem, I'm going to substitute a 5/12 h. And because, what happened there? 5/12 h. And because it's squared in the formula, I square it as well. And there's the h that follows in the formula. All right, let's clean it up. Uh-oh, I'm running out of video. I will have to charge this and charge my camera and finish this a little later. But I'll go until it goes black, but you'll know that I'm coming back to finish this problem. All right, so I'm going to do dv dt, just clean it up, equals 1/3 pi squaring the 5 and the 12. I get 25 over 144. H squared and h I'll combine and get h to the 3rd. Now I solved that. Actually, let's just leave it like that, because we can now finish our derivatives. We were coming across doing our derivatives. We did this one. This 1/3 pi, and now the 25 over 144 is just a constant. And I'll combine those now. dv dt equals 25 pi over 3 times 144, which is 432. And now I'm going to take the derivative, 3h squared dh dt. Alright, I'll combine the 3 and the 25, and make it a 75 on this step so I don't have to rewrite. Alright, now I'm going to substitute in everything I know and solve for what I don't know. I know that the change in volume with respect to time is this 10. 75 pi over 432. And then h is, at the time of h is 8. It's squared. dh dt. So I know everything except what I'm looking for. So if I take all this and put it on the other side, I get dh dt equals, I did all this ahead of time, and it's simplified down to 9 pi. How did the pi get up there? Pi has to be downstairs. 9 over 10 pi. Alright, so verify that that's true, and that is in feet per minute. Alright, so I didn't really run out of tape, so I will not come back on part 2. I just want to show you what to do when there's two variables. You're going to have to find another relationship within the problem so that you can substitute one for the other and work this problem in two variables, I recommend. So, alright, good luck with that, and I will give you some practice on these tomorrow. Till then, good night.